Good day, learners. Welcome to our Physical Sciences lesson. My name is Amenem Kize. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. We are going to focus on knowledge area mechanics today, and then under mechanics we are going to focus on Newton's laws and application. But under Newton's laws, we are only going to focus on Newton's third law and Newton's law of universal gravitation. Right, learners, according to our examination guideline, this is how we have to state Newton's first law, Newton's second law, or this is what we need to cover under Newton's first and Newton's second law. So we did talk about that last week. So our focus is here, Newton's third law. This is how we have to state Newton's third law in words. When object A exerts a force on object B simultaneously exerts an oppositely directed force of equal magnitude on object A, right? And also, under Newton's third law, we must be able, after this lesson, we must be able to identify action-reaction pairs, right? Then Newton's law of universal gravitation. This is what we need to cover under Newton's law of universal gravitation according to our examination guidelines. State Newton's law of universal gravitation as each particle in the universe attracts every other particle with a gravitational force that is directly proportional to the product of the masses and inversely proportional to the square of the distance between their centers. So also solve problems using the equation F equals to gm1m2 over r squared. Calculate acceleration due to gravity using the equation G equals to capital letter Gm then over r squared. And also describe weight as a gravitational force exerted by the earth on an object. Describe mass as the amount of matter in a body measured in kilograms. So we need to know the difference between mass and weight. Also calculate weight using the equation weight equals to mg. Explain the meaning of weightlessness, right? So this is what we need to cover under Newton's law of universal gravitation, right? So content to be covered, I've already explained. We are not going to focus on Newton first and Newton second. We did that last week. So today our focus is Newton's third law and Newton's law of universal gravitation, right? This is the table of constants, which I believe all of you have it. If you don't have it, it is there on your examination guidelines. So there are important constants here that we are going to look at. For example, acceleration due to gravity on planet Earth. It's a constant. The symbol is small letter g, and then the value is 9.8 meters per second squared. Gravitational constant, which is capital letter G, which is 6.67 times 10 to the power negative 11 Newton square meter per kilogram squared. Ne? Then radius of the Earth, which is 6.38 times 10 to the power 6 meters, and then also the mass of the Earth. The last one there, the mass of the Earth, okay? Mass of the Earth, which is 5.98 times 10 to the power 24 kilograms. So these are the constants that we're going to focus more on, or that we're going to deal with today. It's our gravitational acceleration, and then gravitational constant, radius of the Earth, and also what mass of the Earth. All right. Then, so I believe all of you learners, you have this table of constants in your exercise books, right? So when you look at the physical sciences exercise book, whether we are doing grade 10, we are doing grade 11, we are doing grade 12. So what we are expecting to see at the front of your books, learners, is the ATP, right? We are also expecting to see, the examination guideline per topic, right? For example, if we are dealing with with Newton's laws, right? So what are we expecting before you start with Newton's laws? We are expecting, the printout from the examination guideline that talks to Newton's laws, all right? And then we are also expecting the data sheet. So those are the things that you need to have on your exercise book, all right? Is the ATP at the front, is the examination guideline per topic, and also the data sheet, all right? So it's what we're expecting, so that you don't actually memorize these constants, because even when you're writing a control test, or you're writing either it's a formal or informal test, you will be given this table of constant. Same with the data sheet, which is the formulae or the equations that we are supposed to use. For example, when we are dealing with what Newton's second law, we are dealing with what Newton's law of universal what gravitation. So these are the equations. F net equals to ma. We are all aware that the equation is for Newton's second law. F equals to gm1 m2 over r squared, and then that one is for Newton's law of universal gravitation. Mu s equals to fx max over what? Over n, which is the coefficient of static friction, equals to maximum static friction divided by what? The normal force. And also mu k equals to fk over n, where mu k is the coefficient of kinetic friction, and then fk is the kinetic friction, and then divide that by n, which is the normal force, right? And then also gravitational acceleration, right? It's g equals to gm over d squared, or g equals to gm over what? Over r squared. So these are the important formulae, or the data sheet that we need to use when we are dealing with what? Newton's laws. All right. Then Newton's third law, as I've mentioned, that today our focus is Newton's third law and also Newton's law of universal gravitation. So learners, according to our examination guidelines, this is how you are supposed to define what Newton's third law. I want to go back, right? So Newton's third law, right? Newton's third law: when object A exerts a force on object B simultaneously exerts an oppositely directed force of equal magnitude on what? On object A. So this is how we have to state Newton's third law, right? So let's stick to the examination guidelines. So according to the examination guidelines, this is how we have to, define Newton's third law of motion in what? In weights. All right. So let's go back to that slide. Okay. Right. Then what you need to understand again when it comes to Newton's third law, right, is the issue of action-reaction pair of forces, right? So you should know that all forces in nature occur in pairs, right? Therefore, an interaction exists between two bodies. This interaction is known as action-reaction pair, all right? So you will be required to identify the action-reaction pair of forces when it comes to Newton's third law, right? So, for example, in this case, we want to talk about action-reaction pairs here. You are having what? A block on top of the table, all right? You are having a block on top of what? Of the table. So the table is in contact with the block, or the block is in contact with what? With the table. So we want to identify the pair of forces, action-reaction pair, right? So the action-reaction pair, remember according to Newton's third law, right? When body A exerts a force on body B will simultaneously exert an oppositely directed force of equal magnitude on what? On object A, right? So A and B, they're in contact. So which means that when you talk of the pair of forces or action-reaction pair of forces here, it will be a force exerted by the block on the table, and then the force exerted by what? By the table on what? On the block, right? So the action-reaction pair here, right? Okay, it will be, there is a table there and the block, right? So it will be the force exerted by the block on the table, and it goes together with what? The force exerted by the table on the block. So these are action-reaction pairs. Ne? So these two bodies, they exert forces on each other, right? So there's a force exerted by what? By object A on object B, and at the same time object B exert a force on what? On object A. All right. So here my object A, let's say, is the block, and then my object B is what? Is the table. So there will be what? A force exerted by the block on the table, and then the force exerted by what? By the table on what? On the block. So that is the first what? Action-reaction pair of forces here, right? So another thing that we need to be careful about here, right? If, for example, we are only focusing, so for these two forces, right? We are focusing on the table and the block. So that is why we said the action-reaction pair of forces is the force exerted by the table on the block, and then the force exerted by the block on what? On the table. Right. And remember, these two forces, this is very, very important again, learners. These two forces, right, they are equal in magnitude, but they are acting in opposite what? Directions. For example, here, this is the table, and then we are having what? The block. All right. So the force exerted by the block on the table is acting downwards. All right. But the force exerted by the table on the block is acting in which direction? Upwards. So this is the force exerted by what? By the block on the what? On the table. And then this is the force exerted by the table on what? On the block. Right. So these two forces, you should know, they are equal in what? In magnitude, but they're acting in opposite what? Directions. So if the force exerted by the table on the block is 50 newtons, even the force exerted by what? By the block on the table will be what? 50 newtons, but in the opposite what? Directions. For example, in this case, for FB on T, force exerted by the block on the block on what? On the table. So this is the force exerted by, I think I made a mistake here. The force exerted by what? Yes, by the block on the table is this one. It should act downwards. Ne? So this one is the force exerted by what? By the block on what? On the table. And then this one. Okay. This one will be a force exerted by the block. So this is the block on the table, and then this one is table on what? On the block. Right. So these two forces, they're equal in what? In magnitude, right? So if the force exerted by the block on the table is 50 newtons, even the magnitude of the force exerted by the table on the block will be what? Will be 50 newtons, right? But those two forces, they're acting in opposite what? Directions. For example, in this case, the force exerted by the table on the block is acting upwards, but the force exerted by the block on the table is acting in which direction? Downwards. So these are action-reaction what? Pairs. Ne? Then another thing that I think we have noticed this. These two forces, although they are equal in magnitude, right? Acting in opposite directions. But these forces, they are not exerted on the same object, right? So they're exerted on different what? Objects, okay? So for example, force table on the block, right? So force table on the block. So this table, sorry, this force is on the block, ne? So force table on the block. So if this is the block, okay? I'm trying to draw a free body diagram here. If this is the block, right? So the force exerted by what? By the table on the block is this one. Force exerted by what? By the table on what? On the block. You can see it's acting what? Upwards, right? Then, if this is the table, so this is the block, and then this is what? The table. Okay? So the force, let me write it up there. So this is the table. The dot represents what? The table. So the force exerted by what? By the block on the table is acting in which direction? Downwards. So this is the force exerted by the block on what? On the table. So you can see that, okay, although they are equal in magnitude, acting in opposite directions, but they are not acting on the same what? Object. Force B on T, force block on the table is on the table, right? and then force table on the block is on the block. So they're equal in magnitude, acting in opposite directions, but they're not acting on the same what object. So it's another thing that is very, very important when it comes to your Newton's what third law, right? One is to state the law correctly according to the examination guidelines. Okay, then also identifying what the action-reaction pairs, right? So action-reaction pair, we are talking about what the pair of forces, which are forces exerted by what? By objects on each other. Ne? For example, here we made an example with what? With the block and what? And the table. Okay, so there's a force exerted by the table and the block, which is equals to the force exerted by the table on, by the block on what? On the table. Right, and again, although they're equal in magnitude, acting in opposite directions, but they're not acting on the same what? Object. Name. So the focus here, it was only two objects, which is object A, the table, the block, object B, which is what? The table. Now let's again focus on what? Focus on what? On the block, right? The block and the earth, right? The block and the earth. So this is the block, okay? So now I'm focusing on which objects now? The block and the earth, okay? Before I was focusing on what? The table and the block. But now is the block and what? And the earth. So if they can say identify the action-reaction pair of forces there, between the block and the earth, right? It will be the force exerted by what? It will be a force. So I'm focusing on what? The block, and what? And the earth, right? So it will be the force exerted by the block on earth, or weight, okay, and then force exerted by earth or weight on what? On the block. So these are other action-reaction pair of forces there, right? For the first example, we're focusing on what? On what? On the block and the surface. Now we're focusing on what? On block and what? And the earth, right? So action-reaction pair of forces, it will be force exerted by the block on earth and the force exerted by earth on what? On the block. Or force exerted by the block on weight and force exerted by weight on what? On the block. Same with the table. So if now we are focusing on the table and the what? The earth. So the table. So this is the table. All right. So there will be a force exerted by what? By the table on what? On planet Earth, or weight. Right. And the force exerted by what? By earth or weight on what? On the table. So these are action-reaction what? Pair of what? Of forces. Okay. So what is important when it comes to your Newton's third law is to state that law correctly. All right. From there, you must be able to identify the action-reaction pairs. Ne? So action-reaction pair, you deal with how many objects? Two objects. And those objects, they will exert forces on what? On each other. And then those two forces, they're equal in magnitude, acting in opposite what? Directions. And again, let's not forget that they're not acting on the same what? Object. I've shown you that. All right. Then this is application again of Newton's what? Third law, right? So here is the combination of Newton's what? Second and Newton's what? Third law. So here you are given what? A system of two bodies, right? You are given a system of two bodies. You can see that there you have object A and object B, and then object A and B, they are what? They are in contact, okay? There's a force that is applied there on that system, all right? So, and we're told that we should ignore what? Friction, right? So first thing that we can do here, we can draw the free body diagram indicating all the forces acting on object A, and the free body diagram indicating all the forces acting on what? On object B. Right, so this is object what? A. Okay, so for object A, you have the gravitational force, you have the normal force, right? You also have what? Force applied, which is this one. We are dealing with what? Object A. Ne? We are having force applied, which is acting to the right. And then there is a force here exerted by object what? B on object what? A. So it's where Newton's third law comes in. There is contact between A and B, so there will be a force exerted by A on what? On B, right? And the force exerted by B on what? On A, right? So this is our free body diagram indicating all the forces acting on what? On object A. So you have the normal force, you have the gravitational force, the force applied, which is this one, right? You also have the force exerted by what? By B on what? On A, which is acting in which direction? To the left, right? Then free body diagram indicating all the forces acting on object B. You have the gravitational force there, you have the normal force, and then there's a force exerted by what? By object A on what? On object B. So object A on B is acting in which direction? To the right. So this force F what F A on B and FB on A, you should know they are equal in what? In magnitude. And you can see they're acting in opposite what? Directions. Okay, so it's where Newton's third law comes in. Between A and B there's contact, so there's a force exerted by what? By A on what? On B, and then the force exerted by B on what? On A. Then you can now do calculations here. You can calculate what here? They wanted us to calculate what? The gravitational force, all right, and also to calculate what? The force the force exerted by what? By A on B, or the force exerted by B on what? On A, and also to calculate what? The acceleration. So it's application of what? Of Newton's Newton's first law, not first law, but Newton's second law, together with what? Newton's law of Newton's what? Third law, right? So it's Newton's second law and what? Newton's third law. Right, so you can now calculate what? The acceleration. You can calculate what? The net force. Okay, so what I wanted to address here with this scenario is the application of Newton's third law. First thing, obvious, we have to draw that free body diagram, and then where these two objects meet, or because those two objects are in contact, then we can apply what? Newton's third law there. All right, so it will be what? Force exerted by A on B, and the force exerted by what? By B on what? On A, right? Then this is a multiple choice question which talks to the action-reaction pair of forces, right? So a car is traveling along a road. The driver has his seat belt on. The driver sees an obstruction in the road ahead and suddenly applies the brakes, right? An action-reaction pair is the force of seat belt on the driver, all right? An action-reaction pair is the force of seat belt on the driver, ne? And the force of the, so they want us to find actually the action-reaction pair of forces, right? So action-reaction pair, they're saying the first one is the force seat belt on the driver. So identify the objects, right, that are exerting forces on each other here, right? Is the seat belt and what? And the driver. Okay? So if the first force is force seat belt on the driver, right? Then the reaction force will be what? Force driver on what? On the seat belt. Ne? So force driver on what? On the seat belt. So driver on the seat, it cannot be. So if it's driver on the seat, right, the objects is driver and the seat. But here they talked about what? The seat belt. All right. So the two objects is the seat belt and the driver. So it will be force seat belt on the driver and the force driver on what? On the seat belt. So for A, it can't be the correct answer because one, we need to check if both objects are there, right? So driver, seat belt, yes, driver is there, but they didn't talk about what the seat belt here. Instead, they've talked about what? They've talked about what? The seat. Ne? Then wheels, road. So it's different objects. Ne? So it cannot be correct. Ne? Driver, yes, is there. Seat belt is also there. Seat belt and seat, no, it's different objects. So from what was given here, it's like we're told that we need to focus on these two objects, which is the seat belt and the driver. So it will be the force exerted by the seat belt on the driver, and then it goes together with what? With the force exerted by the driver on what? On the seat belt. So that is why our answer here will be what? Will be C, right? Then we can identify what other action-reaction pair of forces here, right? So it's wheels on the surface, right? Or earth, ne? So it can be what? Force exerted by wheels on the surface of the earth or earth, ne? Force exerted by earth on what? On the wheels. Okay? Right. Then it can be driver and the seat, right? The force exerted by the driver on the seat, the force exerted by the seat on what? On the driver. It's another action-reaction pair, ne? Right? So, again, if it happens that the car collides with this obstruction, right? It will be, again, a force obstruction on the car, and then the force car on what? On obstruction. So those are action-reaction what? Pair of forces. So one, make sure that you are talking about what? Actually, the action-reaction pair, it involves how many objects? Two objects. So for example, in this case, is the seat belt and the driver. So there will be force exerted by the seat belt on the driver, the force exerted by the driver on what? On the seat belt. So if our object, it was the wheels, right, and the road, right? So those are the two objects that we are focusing on. So it would be what? Force exerted by the wheels on the road, and then force exerted by the road on what? On the wheels. So it's we only talk about how many objects there? Two objects that are exerting what are forces on each other. Those forces are equal in magnitude, but they're acting in opposite directions, and again, they are not acting on the same what? Object. Newton's law of universal gravitation, according to our examination guidelines, this is how we have to state Newton's law of universal what? Gravitation. Okay? State Newton's law of universal gravitation as each particle in the universe attracts every other particle with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between what? Their centers. So this is how we have to state Newton's law of universal what? Gravitation. So please, learners, we are begging you, please make sure that you don't confuse this law with Coulomb's law. So when it comes to Newton's law of universal gravitation, we talk about the product of the masses, but when it comes to Coulomb's law, we talk about the product of what? Of the charges. So we deal with charges when it comes to Coulomb's law, but when it comes to Newton's law of universal gravitation, we deal with what? A product, or we deal with what? Actually the masses. All right. Then, so this is how we have to state Newton's law of universal gravitation according to our examination what? Guideline. Right. So you just highlight it because before your teacher, starts doing this topic, what is it that you need to have is the exam guideline that talks to Newton's law of universal what? Gravitation, and then you just highlight that definition because we are avoiding a situation where you are going to state the law differently. All of us will stick to the examination guideline for definitions. All right. Then, okay, in symbols, F is equal to gm1 m2 over r squared, where F is the gravitational force, right? This is the gravitational force. So it's gravitational force or weight. Right? Why am I saying it's gravitational force or weight? Let's go back to our examination guidelines, right? So describe weight as gravitational force in newtons exerted by the earth on an object, right? Describe weight as the gravitational force exerted by the earth on what? On an object. So weight is gravitational what? Force. Gravitational force is what? It's weight. So if they can say define weight, right? You have to say it is the gravitational force exerted by the earth on an object. The gravitational force exerted by the earth on what? On an object. Okay? So you have gravitational force there, which is measured in what? In newtons. All right? Then G is the gravitational what? Constant. It is there on our a table of what? Of constants, right? And then M is mass of object 1. M2 is mass of object 2 measured in kilograms. And then R is the distance between the centers, right? Is the distance between the centers. You can see here is from this center to this center, all right? So that is R. R, okay, is the distance between what? The centers, okay? So in symbols, F is given by G M1 M2 over what? Over R squared. Capital letter G, it's a constant, right? Which is 6.67 times 10 to the power what? Negative 11, all right? Then let's talk about the relationship now according to the law, right? The relationship between gravitational force and the product of the masses is directly proportional, which means that if the product of the masses increases, right? Okay, gravitational force will also what? Increase. Okay, we can also represent that relationship using what? A graph. I have a graph of gravitational force versus the product of the masses here. So the graph starts from the origin. So it's a straight line starting from the origin, which shows a direct proportionality between gravitational force and what? And the product of the masses. So gravitational force and the product of the masses, they are directly what? Proportional. So if what the product of the masses increases by the factor of 2, it means that even the normal force will increase by the factor of what? Of 2. That is the meaning of directly what? Proportional. All right. So then from this graph, we can identify the variables, the dependent variable, independent variable, controlled variable, and the physical quantity represented by the gradient of this graph, right? So the dependent variable, so the dependent here, variable, it's always along the vertical axis. So in this case is what? Is the gravitational force, which is measured in what? In newtons, right? And then independent, always independent, it's always along what? The horizontal axis. Independent is always along the what? The horizontal axis. In this case is what? The product of the masses, ne? Product of masses, right? Then now I want us to focus on what? The relationship, the physical quantity now represented by the gradient of this graph, ne? Or the relationship, before we move to the physical quantity represented by the gradient of this graph, ne? Okay? The relationship we can see from the graph, F directly proportional to the product of what? Of the masses. You can see your graph, it's a straight line starting from what? From the origin. So I hope you know now the meaning of the F directly what? Proportional. If you can have something like this, your graph, yes, it's a straight line, but it's not starting from the origin. So you can't say the dependent variable is directly proportional to the independent variable. It cannot be, right? But as the independent variable increases, what happens to the dependent variable? Also increases. But there's no direct proportionality. For direct proportionality, the graph must start from the origin. All right. So then the physical quantity represented by the gradient of this graph, or gradient represents what in this case? It represents what? G over r squared. Where is this thing coming from? Look at our graph. We have we have gravitational force. You also have the product of what? Of the masses. Gravitational force and the product of the masses. Where do we get these two variables? From this equation F equals to G m1 m2 over what? Over r squared. And learners, this is a straight line. When it comes to your mathematics, equation of a straight line is y equals to mx plus what? Plus c. But in this case, our c is 0. Our y-intercept here is 0 because the graph starts from what? From the origin, right? So what is it that we need to do? We need to manipulate this equation in a form of y equals to mx, right? What is our y according to this graph? It should be f, right? What is our x according to this graph? It's what? Is m1, m2. So I can arrange the equation like this so that I have y equals to mx, making sure that my y is f, the subject of the formula is f, and then my x is what? Is m1, m2. So I'm arranging it. F equals to what? G over r squared m1, m2. So if I say G times m1, m2, I still have what? G m1, m2 over what? Over r squared. So this is y equals to mx. My y here is f, and that is correct. It's what I'm expecting. Ne? And then my x here is what? It's m1, m2 is also what? Correct. Which means that the gradient, remember m, when it comes to y equals to mx plus c, m is the gradient, right? So it means that the gradient of this graph represents g over what? Over r squared. The gradient of this graph represents what? G over r squared. Then, if it happens that in an exam or in a test you are getting a graph like this one, right? And then, for example, they say identify the variables dependent, independent, right? You will be able to do that because the dependent variable is always along your vertical axis, which is what we call y-axis when it comes to mathematics. And then your independent variable is always along the horizontal axis, which is what we call x-axis when it comes to your mathematics. Ne? So those are the variables, okay? Then the gradient in this case represents g over r squared. So which means that we can use this graph, right? If there were values given here, we can use this graph to calculate the distance between the centers of these two objects, okay? How are we going to do that? We need to start by calculating what? The gradient. And I believe that you know how to calculate the gradient. For example, this point is 0 is to 0, okay? So let's say this point here, okay? This point here, for example, let's say here we are having what? 10. And then maybe here we are having what? 2 times 10 to the power what? To the power 3, right? And they want us to calculate what? The distance between these two objects, okay? How are we going to calculate the distance? Use the graph to calculate the distance, okay? So how are you going to use the graph? First thing, you need to calculate what? The gradient. So I want us to calculate the gradient here. So the gradient, you need how many points? 2 points. So gradient in this case, it will be what? It's going to be what? Change in f, which is your y, over change in the product of the masses, ne? Which is going to be f final minus what? F what? Initial. And then m1, m2 final minus m1, m2 what? Initial. Okay? Then I'm going to use those 2 points, ne? So the final gravitational force is 2 times 10 to the power 3, okay? The initial is 0. The final product of the masses is 10. The initial is what? It's 0. So I'm having 2 times 10 to the power 3 divided by what? By 10. What am I getting there? 2 times 10 to the power 3, divide that by 10, okay? So 2 times 10 to the power 3, I'm dividing that by what? By 10. Okay, let's check. So it's 2 times 10 to the power 3, ne? 2 times 10 to the power 3. Okay, divided by what? By 10. So here I'm having what? 2000, ne? Which is you divide that by 10, ne? So it will be, yes, 2000, right? So it's 2 times 10 to the power what? Let me just check here. Am I getting 2000? So it's 2 times 10 to the power 3. Divided by 10. No, it's 200. Sorry about that. So it's 200. Okay, that is the gradient. Okay, the gradient is 200, or 2 times 10 to the power what? 2. That is the gradient. Okay, so now I have the gradient, but I know that the gradient represents g over what? Over r squared. So gradient is 2 times 10 to the power 2, or 200. G, 6 times 10, 6.67, sorry about that. 6.67 times 10 to the power negative what? 11. Where is this 6.67 times 10 to the power negative 11 coming from? Let's check. It's a constant, gravitational constant, right? So the gravitational constant is this one, okay? It's 6.67 times 10 to the power negative what? 11, right? So there's no need to memorize it, okay? Then divide that by what? By r squared, okay? So my r squared multiplied by r on both sides. My r squared, it will be r squared equals to what? 6.67 times 10 to the power negative what? 11. Divide that by 2 times 10 to the power what? 2, or divide by 200. Then square root. Remember, we're not looking for r squared, we are looking for r. So introduce square root on both sides. Ne? So I will have r equals to what? Square root of, so I'm having what? A square root of 6.67 times 10 to the power negative 11, right? Divide by 200, ne? Divide by 200. So it's 6.67 times 10 to the power negative 11. So it's negative 11. I'm dividing that by 200, ne? Okay. All right. So here, I will get my answer in what? In meters, okay? I'll get my answer in what? In meters. So what is important here, learners? What I wanted you to understand with this graph, ne, is the relationship between what? Gravitational force and the product of the masses. So according to the law, gravitational force is directly proportional to the product of the masses, right? Then in the form of a graph, this graph shows a direct proportionality between gravitational force and the product of the masses. In this graph, you can identify the dependent variable, the independent variable, the physical quantity represented by the gradient of this graph, right? So the gradient is g over r squared. So you can use the gradient to calculate the distance between the centers, right? Which is what we did. You calculated the gradient, or we calculated the gradient, and for you to calculate the gradient, you need how many points? 2 points, ne? Then from there, get the gradient, and the gradient is equals to g over r squared. Then we can get r, right? We know g, which is 6.67 times 10 to the power negative 11. We already know gradient, 2 times 10 to the power 2 or 200. And then you get r there. Okay, so that is the relationship between what is this? Gravitational force and the product of the masses. Ne? Then mathematical relationship again for the two objects, each of mass m placed at distance r apart, the gravitational force they exert on each other, it's F equals to g m1 m2 over what? Over r squared. So for example, if you're having two objects, ne? Okay, it's object A of mass m, object B or object 2 of mass m, right? And then the distance between the two centers is r, and then the force exerted by m1 on m2 or m2 on m1 is equals to what? F. Which means that if I want F here, it will be F equals to g m1 m2 over what? Over r squared. Ne? So if now the one of the masses is doubled, how will that affect the magnitude of the gravitational force, right? So the gravitational force initially is F equals to g m1 m2 over r squared, but now the distance is being what? Doubled, okay? So if the distance is doubled, right, what will be the new magnitude of F in terms of F, right? So check here is F nu equals to g, then one of the masses is doubled. So it's one of the masses, not r here, one of the masses is what is doubled. So that is why here you can see I'm having what? Twice m1. So one of the masses is doubled. So it's twice m1 m2 over r squared, right? Which is the same as twice g m1 m2 over what? Over r squared, okay? So then the new magnitude of F, it will be what? Twice the original what? Magnitude of what? Of F, okay? So if, for example, the distance, let's say the distance is what? Is doubled, we're going to say, okay, F nu is equals to what? G m1 m2 over r is being doubled, so it will be twice r, all what? All squared. Ne? Then I will have what here? 1 over, if I'm not mistaken, 1 over what here? Over 4 g m1 m2 over what? R squared. Okay, then this is the same as 1 over 4 what? F. Okay, so it's a mathematical what? Relationship between what? Between the gravitational force and the product of the masses, and also between the gravitational force and the distance between, or the square distance between their centers. Ne? So this graph shows the relationship between gravitational force and the square distance between the centers, right? So it's F versus what? 1 over r squared. So the relationship there is also directly what? Proportional. Okay, the relationship is directly proportional. Then the dependent variable here will be gravitational force. Independent variable will be 1 over what? Over r squared. Okay, then physical quantity represented by the gradient is g m1 m2 from F equals to g m1 m2 over what? Over r squared. Ne? So your y in this case is F, and then your x it's what? Is 1 over r squared. Ne? So it will be F equals to what? 1 over r squared g m1 m2. If you say 1 times g m1 m2, you still have g m1 m2 over what? Over r squared. So this is y equals to mx, right? What is, I said g there. My x should be what? I'm making a mistake here, sorry about that. So my x here, it will be F equals to g m1 m2 times 1 over r squared. Y equals to mx. My x should be 1 over r squared. My y should be F. So the gradient represents what? G m1 m2. You can also use that gradient to calculate the mass of each object. If, for example, you are told that the mass of m1 is 5, find the mass of m2. Or the the objects are identical, which means that they're having the same mass, then you can also get what? The mass of each object using the graph. Okay, so this graph shows the relationship between what? F and 1 over r squared. So these are some of the things that are very, very important when it comes to Newton's law of universal gravitation, showing the relationship graphically, okay, and also showing the mathematical what? Relationship between F, which is the gravitational force and the product of the masses, and also between what? F and the squared distance between the centers of those objects. Okay, so here what is happening here, the distance is doubled, ne? So I've done that already. If the distance is doubled, it means that where there's r, you'll substitute by what? Twice r. Okay, then if it's twice r, then we'll have what? 1 over 4. Where is this 4 coming from? Is 2 to the power 2, which is what? Which is 4. Then it will be 1 over 2 gm1 m2 over r squared. And what is this gm1 m2 is f. So it will be what? 1 over 4 what? 1 over 4 f. All right. So that is the mathematical what? Relationship. And mostly you get such questions when it comes to your multiple choice questions, right? Whether it's grade 11 or grade 12, you can get such what? Multiple choice questions. All right. Then calculations now using f. Remember previously we were looking at what? The relationship, ne? Using graphs, and also the mathematical what? Relationship. So I've shown you that. Now let's focus on what now? On the calculations. Learners, when it comes to this equation, there's a lot that we can calculate. For example, if you are given the mass of object 1, mass of object 2, and the distance between the centers, we can calculate the gravitational force, right? Then if you are given one of the masses, you are given the force, you are also given the distance, you can calculate again m2 or one of the masses. You can also calculate what? The distance between what? Between the centers, right? So here they want us to do what? To calculate the gravitational attraction between Earth and what? And the moon. So the mass of the Earth is given as 6 times 10 to the power 24 kilograms. Remember, if it's not given, remember it is there on our data sheet or on our table of what? Of constants, which is 5.98. Right, for 5.98. Let me show you 5.98. Yeah, so mass of the Earth 5.98, right? Radius of the Earth 6.38 times 10 to the power 6 what? Meters. All right, then so there's no need to memorize those two values, right? The mass of the Earth and the radius of the Earth, right? But in this case, they want us to use their values, all right? These two values. 6 times 10 to the power 24, that is the mass of the Earth. And then the mass of the moon, 7.35 times 10 to the power 22. And then the distance between the centers, because it should be the distance between the centers, is 3.8 times 10 to the power what? To the power 8. They want the gravitational force of attraction, right? So every particle in the universe attracts what? Every other particle. All right, so the equation you can see is F equals to gm1 m2 over r squared. Where are we getting this equation from? From the data sheet. So there's no need, learners, to memorize this equation. Just know when to use it. All right, so it's there on your data sheet. Just copy it as it is, and then you will get marks for doing that. All right, then G is 6.67 times 10 to the power negative 11, and then mass of the Earth is 6 times 10 to the power 24. And then the mass of the moon, 7.35 times 10 to the power 22. And then the distance between the centers is 3.8 times 10 to the power 8 meters, but all squared because of that r squared. Okay, so we have to square that. And then the gravitational force will be 2.03 times 10 to the power 20 what? Newtons. Attraction. So there's attraction between those two objects, which is the Earth and what? And the moon. So learners, I want to show you something also here when it comes to this equation. Right, so a gravitational constant, it's 6.67 times 10 to the power what? Times 6 to the times 10 to the power negative 11, ne? Newtons square meter per kilogram squared, ne? So when it comes to the equation, it's F equals to G m1 m2 over what? Over r squared. F should be in what? In newtons. R, which is the distance, it should be in what? In meters. M, which is the mass, it should be in what? In kilograms. So when you're dealing with this equation, make sure that force is in newtons, distance, which is r, is in meters, m, which is the mass, it's in what? It's in kilograms. So in a case where you're given distance in millimeters, you need to convert it to what? To meters. In a case where you're given what? Mass in grams, you need to convert that to what? To kilograms. So it's another thing that is very, very important. So if you have forgotten, just go straight to your data sheet or to your table of constants, then check, okay, this is because this is a constant. So I'm having n what? Meters and kilograms. It means that force must be in newtons, mass must be in kilograms, and then distance must be in what? In meters. So you can use that as a reminder. Okay. All right. Then another question. This is an activity, learners. So let's check. Gravitational force exists between the sun and the earth. So these are the two objects, the sun and what? And the earth. All right. So if a question can say, talk about action-reaction pair of forces there. There will be a force exerted by the sun on earth, the force exerted by earth on what? On the sun. So those are action-reaction pair of forces. Okay. First question, they want us to state Newton's law of universal what? Gravitation. Right? State Newton's law of universal gravitation in what? In weights. So you use your examination guidelines. Each and every particle or every particle in the universe attracts every other particle with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. All right? So that is how we have to state Newton's law of universal what? Gravitation. 1.2. The mass of the sun is 330,000 times greater than that of the earth. All right? The distance between the centers of the sun and the earth is 1.38 times 10 to the power 9 meters. The distance between the centers, they are saying between what? The centers of the sun and the earth, it's 1.38 times 10 to the power 9 meters, right? Calculate the gravitational force that the sun exerts on the earth, right? So the gravitational force, the equation, F is G m1 m2 over what? Over r squared, which is going to be 6.67 times 10 to the power negative 11. Mass of the earth. We know the mass of the earth from the data sheet. Ne? You get it from the data sheet. So you can't say you are not given the mass of the earth. It's there, right? It's 5.98 times 10 to the power what? 24. Multiply that by the mass of the sun. What are they saying here? Are we giving the mass of the sun? They are saying mass of the sun is 330,000 times greater than that of the earth. Ne? So which means that here the mass of the sun will be 330,000 greater. Okay? 330,000 times greater. So we multiply this 330,000 by 5.98 times 10 to the power 24. So this is going to give us what? The mass of the sun. From the statement, we are told that the mass of the sun is 330,000 times greater than that of the earth. So that is why here I said 330,000 times 5.98 to the power 24. Divide that by the distance between their centers, which is 1.38 times 10 to the power 9. All squared. Please, learners, let's not forget that square. All right? It's there. Most learners, they lose marks there. They will write the equation correctly. F equals to G m1 m2 over r squared. But when it comes to substitution, they forget to put that square. If you forget that, obviously you are going to lose almost, I think, 2 marks. Ne? Right. Then, so you cannot afford to lose those marks. Then what will be the force here? So let's check here. the force will be 4.13 times 3, ne? 4.13 times 3, which is 12. Let me just check. 4.13 times 3, which is 12.39 or 1.239, ne? So it's 1.239 times 10 to the power what? 26 what? Newtons. Right. So we are using the equation F equals to G m1 m2 over what? Over r squared. Ne? So what is important here is to know that when we are dealing with planet Earth, for planet Earth, we are given gravitational what? Acceleration, which is 9.8 meters per second squared. We are also given the mass of it, which is 5.98 times 10 to the power what? 24. We are also given the radius of it, which is what? 6.38 times 10 to the power 6 what? Meters. Ne? Right? Then, another thing that I want us all to look at, I think this question addresses that. Okay? How will the gravitational force that the Earth exerts on the Sun compare to the answer to question 1.2? Right? Only greater than, less than, or equals to. So for 1.2, we're calculating what? Calculate the gravitational force that the Sun exerts on Earth. Ne? The Sun exerts on what? On Earth. So the force exerted by the Sun on what? On Earth. Right? What did we get there? We got 1.239. 1.239 times 10 to the power what? 26 what? Newtons. Okay? Then how will the gravitational force that the Earth exerts on the Sun compare to that to the answer to question 1.2? So the force exerted by the Earth on the Sun now is still the same. 1.239 times 10 to the power 26 what? Newtons. So this is application of Newton's what? Third law. Right? So this is application of Newton's third law, action-reaction pair of forces. The force exerted by the Sun on Earth is equal to the force exerted by the Earth on what? On Sun, but acting in opposite what? Directions. So if the force exerted by the Sun on Earth is 1.239 times 10 to the power 26 Newtons, even the one exerted by the Earth on what? The Sun would be 1.239 times 10 to the power 6 what? Newtons, but in the opposite what? What direction. And they're saying here, give a reason. Ne? So give a reason. You can say the reason will be this is application of what? Of Newton's third law. A force exerted by the Sun on Earth will be equals to the force exerted by what? By the Earth on what? On Sun, but acting in opposite what? Direction. So it's application of Newton's what? Third law. So the answer there is equals to. Why is it equals to? Is Newton's third law is what? Is obeyed. Okay, Newton's third law is what? Is obeyed. So when it comes to this activity, what is it that we can talk about here, or what is it that we can get from this activity? Is that if the one of the objects is the Earth, you should know for Earth we are given three constants, right? We are given the gravitational acceleration, we are given the mass, we are also given what? The radius. That is very, very important. Okay, right. Then again, action-reaction pair of forces. We are talking about two objects here. We are dealing with two objects, the Sun and the Earth. So you should know that there's a force exerted by the Sun on Earth, and there's a force that's exerted by what? By Earth on Sun. Equal in magnitude, but acting in opposite what? Directions. So that is application of Newton's what? Third law. Right. Then acceleration due to gravity. Acceleration due to gravity on planet Earth, we know, is G equals to 9.8 meters per second squared. But we can prove that, okay? We can calculate that, although it is a constant. Ne? Learners, how can we calculate acceleration due to gravity? Ne? Acceleration due to gravity, we can use the equation weight equals to mg, right? This g is acceleration due to gravity. This is the mass of an object, and then this is going to be what? Weight. Another equation that we can use, and this equation is there on your data sheet, right? It's g equals to what? G m over what? Over r squared. So please be careful, learners. When it comes to this equation for calculating acceleration due to gravity, g is acceleration due to gravity, which is measured in meters per second squared, and it is always acting towards the center of the planet, right? Then this capital letter G is a gravitational what? Constant. This m is mass of the planet. So if you're dealing with planet Earth, right? So that m will be what? Mass of planet what? Earth. Okay? What about this r? R is the radius of what? Of the planet. Okay? For example, if you're dealing with what? Planet Earth, then r will be the radius of what? Of the Earth. So what I want us to do here, before this question, this is what I want us to look at. Okay? We want to calculate gravitational acceleration on planet Earth. We already know that is 9.8, but let's confirm if sure it is 9.8. So remember, when it comes to this equation, learners, right? This is gravitational acceleration on planet Earth, and then this is gravitational constant, and then this is mass of the Earth, and then this is the radius of the Earth. So G, capital letter G, is this one, and then mass of the Earth, it's 5.98, ne? 5.98 times 10 to the power what? 24, which is approximately what? 6 times 10 to the power what? 24. The distance, not the distance, but the radius of the Earth, right? The radius of the Earth, it's 6.38 times 10 to the power 6, but it's all squared. So when you calculate there, you will get what? 9.8 meters per second squared, right? 9.8 meters per second squared. So please be careful, learners. When it comes to this equation, that m is the mass of the planet, that d, that r is the radius of the planet. Okay, then let's go back to this question. So this question is about proportionality, okay? Using G equals to what? G m over r squared, okay? So if you're having G versus what? Mass of the planet, the relationship will be directly what? Proportional, okay? The relationship will be directly what? Proportional, keeping the distance constant, okay? Then the gradient will represent what? G is equals to what? G over what? Over r squared times what? Times m. So it's y equals to mx. So your x, it's mass of the planet, and then your y, it's what? Is gravitational acceleration. Then the gradient will represent what? G over what? Over r squared. And then G directly proportional to 1 over what? Over r squared. Then G here, if here we have 1 over r squared, the relationship will be directly what? Proportional. Which means that gradient here will represent what? We have G equals to G m over r squared. So it will be G equals to what? G m times 1 over r squared. So the gradient represents what? Gm. Okay? So that is the relationship between G and m, which is mass of the planet, and G and what? And the radius of the planet. So you can see the relationship there. Then mathematical relationship. Let's check this question. Planet X has a mass twice the mass of the Earth and a radius 1.5 times that of the Earth. If the acceleration due to gravity on Earth is G, then the acceleration due to gravity or gravitational acceleration on planet X will be. So G on planet Earth is G m over what? R squared. Ne? Where m here will be mass of the planet, where r will be radius of what? Of the planet Earth. Okay? Then UG, which is acceleration due to gravity or gravitational acceleration on planet X, right? So on planet X, it will be what? G. We are told that planet X has a mass twice mass of the Earth, ne? So it will be twice mass of the Earth over radius 1.5, right? So it's 1.5 times that of the Earth, ne? So if they're saying 1.5, so 1.5 is something like this, ne? 1.5. Okay? So if it's 1.5, so 1.5, this is the same as what here? 3/2, if I'm not mistaken, right? So 1.5 is the same as 3 over what? Over 2. So which means that here it will be 3/2r all squared. Because they're saying 1/1.5, right? Then I'm having twice GME over 9/4. Because it's 3/2 squared, ne? All right? Then r squared. And remember, this r squared is the radius of the Earth, which is 2/1 times 4. If I'm not over what? Over 9. Ne? Times 4/9. GME over r squared. Okay? So here I'm having what? 8/9. What is this GME over r squared? It is equals to what? A gravitational acceleration on planet what? On planet what? On planet Earth. Okay? Do I have 8/9g? Yes, I have 8/9g there as the correct what? Correct answer. Okay? So it's mathematical relationship there. We're told that on planet Earth, right, G is GM over r squared. Okay? But on planet X, the mass, it is twice that of the Earth, right? And then what about the radius? Is 1.5, which is 3/2 r. But remember, this is what? All squared. Then you solve that. At the end, you'll have what? 8/9 what? Over 9g. So it's just the mathematical relationship between what? Between g, m, and also what? And r. Okay. Then difference again between mass and weight. You should know the difference. One, all of you know that mass is a scalar, but this is going to be what? A vector. And what is mass? Is a measure of the amount of a substance that is there in what? In an object. So what I want us to do, let's go back to the exam guideline. Right? To the exam guideline. You should know the difference between mass and weight. But it starts with what? The physical quantity, right? Mass is a scalar, and then weight is a what? A vector. So I want us to go back to, So describe weight as the gravitational force in newtons exerted by the Earth on what? On an object. Describe mass as the amount of matter in a body measured in what? In kilograms. So that is the difference between mass and what? And weight. Weight is the gravitational force exerted by the Earth on what? On an object. And then what about the mass? It is the amount of matter in a body measured in what? In kilograms. So weight, it's a gravitational force exerted by the Earth on an object, and it is measured in what? In newtons. And the mass it is what? The amount of matter in a body measured in what? In kilograms. And again, in addition, weight, it's a vector, and then mass, it's what? It's a scalar. All right. So that is the difference between what? Between mass and what? And weight. So just use your examination guidelines to explain that difference, right? Weight, gravitational force exerted by the earth on an object, it is measured in newtons. It is what? A vector. Okay. What about mass? It is the amount of matter in a body that is measured in what? In kilograms, and it is what? A scalar. And then that's it. Okay. Then okay, let's go back. Okay, again, explain the meaning of weightlessness. Right. So weightlessness, according to our examination guideline again, right? Weightlessness is just a sensation. It's a feeling, right? Explain weightlessness as the sensation experienced when all contact forces are what? Are removed. So it's just a feeling, experience when all what? The contact forces are being what? Removed, right? So if all the contact forces are being removed, it's when a person will what? Will experience what? Weightlessness. Okay? So for example, I want to give you an example. I think you have noticed this. If you're in a lift and the lift maybe is going down, you feel weightless, right? Why do you feel weightless? It's because all what the contact forces are being what? Are being removed. For example, your normal force is being what? Is being removed. The only force that is left, or the only force that is exerted, is what? Is the gravitational force. So what am I trying to say is this, learners. If the only force exerted on an object is the gravitational force, which is what? A non-contact force, there are no contact forces, the object will experience what? Weightlessness. Ne? So the object will experience weightlessness if the only force exerted is the gravitational what? Force. But when they say explain weightlessness, what are you going to do? Use the examination guideline. It is just the sensation experienced when all the contact forces are being what? Are being removed. So I'm giving you an example, right? An example will be if the only force exerted on an object is the gravitational force, which is the non-contact force, the object will experience what? Weightlessness. So we have talked about the difference between mass and weight. Then now you know if we are talking about weightlessness, what are we talking about? Ne? So you experience weightless if the only force exerted is the gravitational what? Force. So in that that moment, it's like all the other forces or all the other external forces that are being what? Removed. Ne? So but please, when you explain weightlessness, use the examination guidelines. So according to your examination what? Guidelines, weightlessness is explained as the sensation experienced when all the contact forces are being what? Removed. That is how you have to explain what? The term weightlessness. It's just a feeling when the contact forces or all the contact or all the external forces are being what? Removed. For example, if the only force exerted is the non-contact force, such as your gravitational force, then the object will experience what? Weightlessness. Okay. And then, so it's still weightlessness here. Then let's look at this question. Two satellites orbiting the Earth are situated on opposite sides of the Earth. Satellite A has a mass of 3,800 kilograms, and then satellite B has a mass of 4,500. Satellite A is at a height of 25,000 kilometers above the surface of the Earth. above the surface of the earth, right? Above the surface of what? Of the earth. That is what? Satellite what? A. Okay? And then first question is to state Newton's law of universal gravitation, which I believe all of us, we should know it by now. Then explain the term weightlessness. What does it mean? It is just the sensation experienced when all the contact forces or all the external forces are being what? Removed. That is weightlessness. All right. Calculate the force between the Earth and satellite A. Okay, let's go back to the statement. Right? So the equation obvious will be F equals to G m1 m2 over r squared. We know the mass of the Earth from the data sheet. We are given the mass of what? Of the satellite. Your two satellites orbiting the Earth are situated on opposite sides of the Earth, as you can see in the diagram. Satellite A has a mass of 3,800, né? And then the distance, they're saying it is at a height of 25,000 kilometers above the surface of the Earth. So now the focus is this satellite and the Earth, okay? So here, from the center of the satellite, this is the satellite, right? Let me just do this. From the satellite to the surface of the Earth is 25,000 kilometers. Ne? The mass is 3,800 kilograms. The mass is 5.98 from the data sheet, ne? Times 10 to the power what? 24 kilograms. Okay? So they want us to calculate the force. Okay? Calculate the force between the Earth and satellite A. Right? Earth and satellite A, F equals to G m1 m2 over r squared. Ne? So G 6.67 times 10 to the power negative 11. Mass of the Earth is 5.98 times 10 to the power what? 24. Mass of the satellite is 3,800 what? Kilograms. Ne? Then what is the distance now between the centers? This is very, very important. Is the distance between what? The centers. So is the distance given that 25,000 kilometers between the centers? No. It's from the center of the satellite, which is the satellite A, to the surface of the Earth, right? But the distance, it should be from center to center. So here, we need to add the radius of what? Of the Earth, so that we have that R, the distance between what? The centers, right? Then I will have what here? 25,000 kilometers. Now, according to what this equation, we are expecting the distance to be in what? In meters. So you convert kilometers to what? To meters, right? So how do we convert kilometers to meters? We multiply by what? By 1,000, which is times 10 to the power what? 3, plus 6.38 times 10 to the power what? To the power, let's just check its power what here? 6, ne? Let's confirm. Is it power 6 or power 8? Because there's no need for us to memorize it, ne, learners? It's power 6, yes, it's power 6. Okay? Right. So all squared. So I hope you understand why I added RE there, radius of the Earth, because the distance is should from center to center. But that 25,000 kilometers was from the center of the satellite, which is satellite A, to the surface of the Earth. Then for us to get center to center, that distance, we need to add the radius of what? Of the Earth. Then we'll get our F in what? In newtons, which is, in this case, they got what? They got 1,539.23. 1,539.23. Okay, so what was important here is the issue of RE, distance from center to center. So it's what I wanted to address with this question, right? Then 2.4, what distance above the surface of the Earth should satellite be to experience the same force towards the Earth as satellite what A? Choose from greater than, less than, equals to the distance above the Earth. Explain how you arrived at your what? At your answer. What distance above the surface of the Earth should satellite B be to experience the same force towards the Earth as satellite what? A. All right? So here it should be what? Greater than. Okay? Why is it supposed to be greater than? Okay? So greater than the mass. Okay, so here, let's check. What distance above the surface of the Earth should be satellite B to experience the same force towards the Earth as satellite what? A. Is the distance supposed to be greater than, right? Less than or equals to, right? Right. Then let's go back. Let's check we want the force experienced by satellite A on Earth to be equals to the force experienced by what? Satellite B on what? On Earth. For that to happen, it was going to be easy if the masses were the same, right? Okay? So if the masses were the same, right? So if the masses were the same, right? And then the distance were also the same, we're going to say what? Yes, if the masses were the same, we're going to say the distance should be what? Should be the same. But now the masses are not the same. Check the mass of satellite B is 4,500, right? So it's greater than that of what? Of satellite what? A. So to maintain the same force that satellite A exerts on what? On Earth, to be equals to the force that satellite B exerts on what? On planet what? On planet Earth. Then here we are expecting the distance to be what? To be greater, because the distance to be greater than, because it has what? A greater what? A greater mass. Ne? Okay, and for the same force, the distance must also be what? Must also be greater. So they are using what? The relationship between what? The product of the masses and the square of the distance between what? Between their centers. Right. So I think for today we are done. We'll still continue doing Newton's law of universal gravitation next week. Ne? So, but for today, I think we have done justice, and then we'll see next week. Thank you so much.